So we have this, all four lines are parallel, L1, L2, L3, L4. And also we have a transversal that the transversal, the four parallel lines are arranged in such a way that AB is congruent to BC and congruent to CD. So given that condition, if you just draw any arbitrary transversal across the power lines, then this has to be true. That means this segment is congruent to this segment, is congruent to this segment, or this is congruent to that or that. So let's give a letter to it so we just pick this as this line as example. The A, B, C, D, E, F, G, H. So conclusion. And it's actually something we need to prove, that is ED is equal to, EF is equal to FG, and that is equal to GH. All right, so how do we prove that? So remember, in Euclidean geometry, the congruency of triangle plays a very, very important role. You find that we use that a lot. So in this case, the way we prove it is like, we are going to draw lines parallel to this from here. And that we know we can draw it, because we know how to draw a parallelogram. So that basically become a parallelogram here. This and that's a parallelogram. Then we can do the same thing here. Draw a parallelogram. And same here, draw a parallelogram. And now what you can see, so now we're going to looking at we're looking at those triangles here. As long as we can prove the triangles are congruent, then we can prove that conclusion, because this is a side of the triangle, this is a side of the triangle, this is a side of the triangle. Okay, so now we just pick any one to prove it, because the process is the same for the other. Now, if we pick this one, and you can see that let's pick this one and that one. Let's call this one A, B, C, D, H, I, and J. So we know EI is equal to AB, but AB is equal to BC, and we know BC is congruent to FJ. So that means we know this and that are congruent. Okay. And now we also know so we know this, let me see. So therefore EI is congruent to FJ. So we got one side now. So we're going to use angle side angle to prove it. Now, so this angle, if you continue that, and you'll see that this angle is congruent to this angle, because this line and that line are parallel, and but also this line and this line parallel, so this angle equal to that angle. So therefore, we have one angle congruent, which is EIF congruent to angle FJG. We just need one angle. We need this angle. So how do we prove this angle is congruent? And we know that this line, that line are congruent. So therefore, this angle and that angle are congruent. And we can also, based on the parallel line, that we can prove this angle and that angle are congruent. So if the whole angle are congruent, and also part of the angle are congruent, then the other part has to be congruent. So therefore we can prove I, E is, we're talking about, use different lines here. We're talking about this angle and that angle are congruent. So IEF now it's congruent to JFG. So now we have angle. We know this angle, we know a side, this side and that side, and we know this angle and that angle. So we got angle, side angle. So therefore, the triangle EIF is congruent to triangle FJG. And because those triangles are congruent, so therefore, so the property of the congruency of two triangles is that all sides are congruent. So therefore EF is congruent to FG. So basically that's how we prove it. So if this and that are congruent, now the logic conclusion is that this and that has to be congruent. So that's how we can prove that this theorem. And that just doesn't matter how you do it. Doesn't matter how many parallel lines. Let's say if you have, and if you put this line here, and this is congruent to this line segment, all congruent, then no matter how you draw it, then this congruent to this line. We are not saying this is the same as this length. We are saying on this line, the parallel lines cut it in the same, cut them to equal segment, because we know this. Because it cut one line into equal segment, it will cut any transversal lines into equal segment. So this will be, and that, and that. Good?
Yep.
Any question here?
Nope.
Okay. So now we're going to see another theorem, which is basically the application of this theorem, is that how do you actually cut something into equal, like say, if you got line segment, how do you cut them to equal? Now you cut to half, that's easy. We know how to do that. We can draw a perpendicular bisector. We can cut to half. We can cut this to half. We can cut this half. That we know already. That's actually is not difficult. But how do we go about? Where is my? So how do we can do something like arbitrary? So far we know, as long as we can cut to half, a quarter, or 1/8, we can do that. But how do we do like 1/3 or 1/5 or 1/6 or 1/7? How do we do that? And that actually is, if you look at it, all you have is a straight line and the compass. So there is no way for you to measure. And the very important thing, Euclidean geometry, is there is no measurement, because our straight edge has no marker. It just draw a straight line. That's all it can do. And the compass also has no measure. We cannot say the radius is how many inch. We cannot say that because there is no way for us to measure. And back then, think about more than 2,000 years ago, I mean, if they can measure something, it's probably very inaccurate, very just like kind of very rough figure. So how do we do that? So how do we say, okay, how do we cut that into say equal each one to 1/5 of the length. Oh, 1, 2, 3, 4. Well, even to draw it, it's going to be hard to draw because now this is bigger than 1/5. Even to draw it, it's kind of hard. But how do we do that? So let me open up the Desmos, which we can see how to do that. Okay. All right. Go back to Desmos. Okay. So we have a line segment, and we want to cut them into 1/5 on each. Cut them into 5 equal length segment. So what we're going to do that is we're going to draw a line which we call the 8 line. It doesn't matter where that goes. So just arbitrary. Okay, let's do it here. So now what we can do, we know we can draw a circle. Okay. And now we can just keep drawing that circle which have the same radius. And that's kind of easy to draw because we know the point. Just pick here, here, pick here, here. Now, how many line segment we have? We got 1, 2, 3, 4, 5. Okay, we actually don't even need this one. Okay, we got 5 already. So let me do that. Oh, I need to. Oh, sorry, I didn't even share that. Let's redo it. I forgot to share that to you. Okay, let's redo that. Okay, we got line. Can you see my screen now?
Yeah, now I see.
Okay, so we got line segment, and we're going to cut that line into 5 equal length. So what we're going to do is we're going to draw a larger line. We can do that. We can draw a line, we know, and we can draw a circle. So we just go. So that's kind of arbitrary. It doesn't matter how big we have, as long as we have enough space. So let's draw that. 1 circle. And we can draw that because we have, and we go start here. We find here. Start here, go here. Now we got 1, 2, 3, 4. Just one. Okay. So I have that. And you will notice that we got 1 here, 1 here, 1 here, 1 here, and 1 here. So we cut this line in. Well, we're not cutting this line. We just we find the 5 equal length on this line here. Let me see if we clear that, hide it, hide it. Okay, we got the points there already. Okay, hide it. So now we have we got 1, another 1, 2, 3, 4. Oh, where's our 5? 5 shouldn't be there. Let's go back. I think I didn't put the points there. That's why I have the problem. So it should be here. should be here. Then I can get rid of this line here. Okay, so we got 1, 2, 3, 4, 5. Good. Hello? Hello, I guess okay. Hello. Hello.
Yeah.
Hello. So we got a line here, and then we put this line, it's called 8 line, and we got circle. Hello, can you hear me?
Yeah.
Okay, 1 and that, because we know the points here, that we can easily do it. We can draw a circle like that. And now we see how many we have, how many lines we have. We got 1 here, 2, 3, 4, 5. Now we have that. Let's just put some points so we can show that. 2, 3, 4, 5. And then we can, hey, that's not it. We can take this out, this out, this out, this out, this out. So we can hide all that. So now you can see the points there. So what we're going to do now is to draw a line segment from here to here. That we can do. And we draw parallel lines from here. Okay, this actually, we can do that in, there's tools for that. We know we can draw that, just use a line and just using straight line and compass. But with modern technology, we can just use the convenience here. So we got find the line, then find the point. We can do another one. And okay, we got one. Click line, find another one. No, another one, another one. So we can draw this line here. So once we've done that, and based on the theorem we just learned, because there's another parallel line. Okay, because of the theorem we just learned that, we know those parallel lines cut this line. Let me do that. So we got 6 parallel lines. 1, 2, 3, 4, 5, 6. And those 6 parallel lines cut this line. Cut this line into 5 equal parts. 1, 2, 3, 4, 5. So therefore, this line is also a transversal of the parallel lines. So therefore, by the theorem, we know this has to equal to that, has to go to that, has to go to that, has to go to that. So that way, we just cut this line segment into exactly 5 equal length. Good? Yeah, I guess okay.
Yeah.
Okay, so here is something you can try as a homework. Just did what I did, but this time you're going to cut that into 7. Good? Cut into 7 equal length, given any line segment, and cut that into 7 equal length. Good?
Yep.
Mm-hmm. All right, so I'll see you next week.
See ya. Alrighty, thank you.
Okay, bye.